Okay, I know this is all your favorite activity, reviewing homework problems. So on this one, we are going to review the system schema and force type problems. And it is really important that you are able to accurately identify forces in a schema, because then that leads to drawing the correct free body diagram. And once you have the correct free body diagram, then you can develop the correct net force equation. And once you have the correct net force equation, then you can solve and get things correct. But it all starts with having knowing the forces or the interactions between objects, which we identify on our schema. So we're going to look at problem number 5, and in here, a nail has been picked up by a magnet. And so the objects that we have are the magnet. We know we have a nail, and we're always going to assume the earth unless it specifies that we are somewhere other than the earth. So once you have the earth, you can always put in the interactions of weight. If you did not put weight between the magnet and the earth, no problem. Now, because it's a magnet, we know that we are going to have a magnetic interaction. So we're going to have a magnet or magnetic. But we also know that we have two solid objects that are touching each other, and they're actually pressed against each other. And so we also have a normal force. And so that is what the system schema should look like. So let's see how people did. So this looks great. The only thing that we're missing is the normal force, because the two things are touching. All right, we like this one. We'll say awesome. Also awesome. Let's do interesting things. Let's do a star. Nice. Okay, we're missing the earth. And so we're going to have either weight or gravitation. Either one of those are fine for me. And we are also, of course, missing the normal force. Okay, water skier. Now, one of the things that will, in physics, we always want to simplify situations as much as possible. And so we're going to assume typically anything that is attached to a person is part of the person. So a couple of you did the skis and the person separately, and that's totally fine. I will talk about those system schema when we get to them. But typically, we're going to say that we have the skier, we have rope, we have water, and we have the earth. And I'm only going to draw the weight between the earth and the skier. The water and the earth are attached to each other, and so I'm not going to worry about that. And then the rope, we are almost always going to assume, actually I think we are always going to assume that ropes are massless, and so they're not going to have a weight interaction. So between the skier and the rope, we know that we have tension. And between the water and the skier, water is not a solid object, and you can only have normal force if you have two solid objects. And so if you drew an interaction but weren't sure what to call it, that's fine. But whenever we have a fluid and then anything else, a solid or a liquid object, then what is between them is called the buoyant force. So people may have put in other things and that would have been fine, but this is the schema that I would have done to make it kind of as simple as possible, but still accurate, and we'll be able to get accurate results or correct results. So let's see what we've done. Okay, so missing the Earth. That's a big one. Technically, it is true that there is a gravitational attraction between any two objects with mass, but this is not going to be significant, and I would not call it weight. So that is not going to go there. We will have weight between the person and the Earth. Between the skis and the person, we're actually going to have a normal force. And skis in water, buoyant, is great. And so if you are going to treat the skis and the person separately, this is what you would put as long as you don't have the weight on it. Okay, so let's go through this one at a time. So the water is not attached to the rope. We can just look at the diagram and see water is not attached to the rope. And so this interaction should not be there. And between the rope and the skier, you can either have normal force or tension. You cannot have both. Tension is a pulling force. Normal is a pushing force. You can't do both of them with the same object. You cannot both push and pull at the same time. And so this normal force should not be here. Okay, between the skier and the water, it looks like they have normal. It looks like that might be a normal, but it should actually be buoyant. Buoyant. And which might be the B. Okay, so if that is B, I'm gonna change my name. That one's okay, but therefore this one should not be here. Friction, again, is something that is only associated with solid objects. In order to have friction force, you must have a normal force, because remember the formula for friction is mu times the normal force. And if you don't have a normal force, you cannot have friction. But what you have with fluids is something called drag. And so if you want to do something friction-like, then you would call this drag. And when I say a fluid, that's either a liquid or a gas. Both of those are fluids. And so you can have drag either on water or in the air. Okay, made a lot of adjustments. And again, typically we will ignore drag unless we specifically mention it. So I'm going to agree. We'll do this in green. So we will agree with tension, gravity, buoyant, and drag. And that's all that I would put on here. Okay, so we've got rope and tension, good. Person and water is buoyant, good. Why don't we have a normal force? Because water is not a solid object. Instead of friction, we're going to call this drag. And weight, and that is good. So, okay. Okay, again, these people chose to put skis in, which is not wrong. It's just we don't necessarily need to complicate it that way. So let's go through one by one and see how we're doing. So skier and skis, I would agree normal. Skier and rope, tension, correct. Skier and earth, weight. Skis and weight, I'm good with that. Water and earth, I'm good with that. Again, we don't need to put it in. Buoyant and water, I'm good with that. Why don't we have a normal force? Water is not a solid object. So that's the only one I would object to. Normal force, you have to have two solid objects pushing against each other. Okay, skier and water, not normal force. We would call it buoyant. And again, no friction. We're going to call this drag. Okay, let me make some corrections. So this should be buoyant. And this should be drag. Again, you do not need to put drag in, but if you do, you can call it drag. We are missing the rope. Okay, so rope. And that we're going to have tension. Okay, so tension and rope, I agree is correct. Person and ski, I agree is normal. Ski and water, I agree is buoyant. Water and gravity, I agree is gravity, but we also need to connect the person is interacting with the earth. We can't like go in a chain and say, oh, the person therefore is interacting with the earth because I've connected all of these. The person needs to have their own interaction, and I'll tell you why. If we are doing a free body diagram with or on the person, okay, so let's draw our boundary. So on the person, we can see that, including what I've drawn, there are 3 forces. But if you only used the initial one before I corrected it, then you would have tension going this way. So force of tension on the person by the rope. And then you would have the normal force, so force normal on the person by the ski. And there would be no interaction with the earth. There would be no weight. And so the person would actually be flying out of the water in this direction, or that would be their change of motion. And so that's why you need to connect. Any object has to be connected directly to the object that it's interacting with so that we can put in all the interactions this object is having. And so that's why I have to connect the person to the earth so that we can put the force of gravity or weight on the person by the earth. So I'm not just being picky, it really needs to be there so that our free body diagram is correct. Okay, dancer leaning on a table. Now, for this one, I asked you to consider the angles and friction. And so what you need to do is think about if the floor is ice, so in other words, no friction, will the dancer hold this position? And if the answer is no, then we know that we have to have friction. Okay. All right, so let's build our schema. So we know that we have the table. We have the dancer. And I'm going to do floor, earth. So floor, earth. Okay. All right, we know that the dancer has weight or gravity, either one is okay. And we know that the table also has to have weight or gravity. And we know between the table and the dancer is pushing against the table, and so we have a normal force. I'm going to spell these out. Weight. Now, we've got to have friction. I forgot to put, okay, the table is touching the floor, so that is going to be normal. And the dancer is touching the floor, so that is going to be normal. Now, if the dancer is leaning in this position, she is going to slide backwards unless she has friction. And so we're going to put in, I'm going to change colors just so you guys can see, but you don't have to change colors. So we know that we have friction between the dancer and the floor. And we also need to have friction between the table and the floor because, again, if there's no friction and she's pushing against the table like that, the table is going to go flying. And so another thing to remember is that, again, if there's friction, there must be a normal force. And we know this from the formula, the force due to friction is equal to the coefficient of friction times the normal force. And so if this is missing, then that has to be missing. Okay. All right, let's see how we did. Okay, so we've got some things. Oh, one of the things you might wonder, do we think that there is friction between the table and the dancer? I would say probably yes. Just because she wouldn't be able to grip it, again, with the angle. So I would probably put friction there too. If you left it off, I would not take off, but it's just something to think about. All right, so we are missing multiple interactions. We know that we have to have normal, and we have to have friction. And we have to have normal, and we have to have friction. Let's make sure I haven't missed anything. 1, 2, 3, 1, 2, 3. Okay, we're good. Okay, again, normal, friction, normal, friction. Okay, here you cannot combine interactions on a single line. And again, we're using this schema to help us build free body diagrams. And so if I do my boundary and I count the number of lines, I count 1, 2. I'm only going to count 2 lines, but this line, people are saying, is representing 2 forces, and so I'm not making good use of my visual aid. And so you cannot combine interactions on a single line, 1 line for each interaction type. Plus, we know we're missing things, so we need to have normal. I'm going to put a separate line for friction, normal, friction, and we have one more issue, not tension, okay? They're pushing against each other. Push is a normal. Tension is a pull. And remember, normal, I hope you remember, means perpendicular. It does not mean typical or common. Okay, so dancer, table is normal. We're good with that. So again, people are combining interactions. You cannot do that. 1 line, 1 interaction. Also, so I need to have, change back to red. So I need to have a separate line for normal. And if there's no friction, she's falling. Here, we've got friction without a normal force. We can't have that. So friction and then normal. Okay, so we've got normal, we've got weight, we've got weight. Okay, and just stylistically, they do normal plus friction and have 2 lines, normal plus friction and have 2 lines. That's kind of interesting. Since they go together, I wonder if I'm okay with that. Usually I draw them separately, but I actually think I might be okay with that notation since you cannot have friction without a normal force. So typically I label them separately, but I might be okay with that. Okay. All right, so so I'm good with that. I am good with that. I'm good with that. Normal and friction have the two interactions, but you need to have two lines, okay? And then forgot about person and floor. We need to have normal and friction. Okay, problem 10, squirrel sitting on the roof. And again, we're going to think about if the surface is ice. So in other words, no friction. Okay. All right, so we've got a squirrel, roof, earth. We know we have weight or gravity. And we know we have normal. What direction does the normal force go? Hopefully you got this correct. It goes up and to the left. That's my F normal, because remember it makes a perpendicular line. Okay. All right, so this is all we have. That squirrel is sliding. And so we know that we have to have friction between the squirrel and the roof. All right, I think we're good. Okay, nice job. Get a star. Nice job. Get a star. Pretty close. We are missing normal. Anytime you have two solid objects in contact with each other, there has to be a normal, or you can say cannot have friction without a normal force. Okay. Because force of friction is mu times the normal force. So if there's no normal force, actually I think I'll do that as an X. If there is no normal force, there is no friction. Yes, good job. Yes, good job. Okay, just missing normal force. All right, hopefully the repetition, you will be able to do schema successfully and put in all the interactions so that you can do the correct free body diagram, because then you can do the correct net force equation, and then you have a good chance of getting a problem correct.